Hello, good evening. Shall we start?
Let us
Wait
start,
for
sir.
wait for another 2 minutes.
Okay.
Okay. I have already shared the Google document link. You can. I have not typed anything, of course. So I don't know. Those who have joined later will be able to see that or not. It's not very clear to me. If you're not seeing that link, please let me know. I can post it once again. So I think we can start now, and let others join during this lecture. So as I told yesterday, I think we were supposed to discuss some problems from calculus using whatever concepts we have discussed so far, like finding limits, checking continuity, differentiation, etc. So one of the most elementary problems that we usually do in calculus is finding maxima and minima. Okay, so which essentially means that we need to find a derivative. We need to check whether some particular points are critical points or not. First of all, we have to determine what are the critical points. Of course, there are critical points. By the definition, it means that they are points at which derivative vanishes or points at which the derivative does not exist. So as we have already seen, for a computing software to find out points where derivative does not exist is a little bit difficult. And most of the times what we have seen is that the functions that we are taking, they will be having derivatives in most of the points, because we assume most of the times continuity, differentiability, etc. But the derivative can become equal to 0. So critical points in our problems, we will try to assume that all the points everywhere the function is differentiable, but derivative vanishes at some points. Only those points are critical points is what we are trying to think, because non-differentiable points, locating such points is a little bit difficult in any computing software. We will try to see if that is possible or not. Okay, so we will try to find the derivative. After that, we will try to equate that derivative to 0. Then we will try to find the critical points. At critical points, we will try to see whether they are the maxima, local minima, absolute maxima, absolute minima, etc. Okay, that's what we are going to focus today. Let me share the screen. So even before that, let us try to look at one particular command called solve. Okay, solve command is required if you try to locate roots of a polynomial or roots of not necessarily polynomial, it can be some other function also. The solve function, solve command or solve function is actually necessary for us. Let us try to see the effect of solve first. Suppose we take f is equal to or f is equal to x square minus 2, suppose. Then f dot solve. Solve is actually for x. We need to probably specify that, or solve f of x equal to 0 to be simple enough and to be intuitive enough. Solve f equal to or f of x equal to 0. F is equal to 0 with respect to solving for x. So what is the solution? Oh, sorry, x square minus 2. Yeah, we are getting the solutions as minus square root of 2 and plus square root of 2. You can see that solve is returning the answer as a list. Okay, so this is essentially a list consisting of two parts. The first part consists of the symbolic notation x equal to minus square root of 2. Second part consists of the symbolic notation x equal to square root of 2. But we are actually interested only in, so that's happening because we are solving for x. So we are actually interested only in this minus square root of 2 and the square root of 2. That x equal to part is not very important for us because we have already made our decision that we are trying to solve it in terms of x. So if we say this solve is returning a list which consists of symbolic notations, we don't want that. We want only the numerical values, minus square root of 2, square root of 2. These are the two things that we want. Now we should make use of our knowledge about list. So this is a list. Okay, let us roots f, suppose that I am giving this name and saving the roots to this. So if I ask for roots f, the 0th one, so this is the 0th element in the list, this is the 1th element in the list. So if I ask for print roots 0, I should get the first root, sorry, roots f. Yes, I am getting the first root. Now if I ask for roots 1, I will be getting the second root. But still the problem is that x equal to part is there. To remove that x equal to part, we will use another command called RHS. See, RHS we know that the right hand side, the usual mathematics meaning. So if we ask for the RHS of both these, RHS, open close bracket. So we are getting minus square root of 2, square root of 2, two roots. This is how we solve for an equation in terms of x. I think I have already shared the Google document link. Let me just update the Google document with this. So update. I am not using the word roots because the word roots, the problem here is that Sage might have already assumed a meaning for what do you call the mathematical word roots. So it's better not to use any of the usual mathematics words because they all might have been already given some meaning in Sage, meaning given by Sage itself. Therefore, we should not that conflict with that meaning, because if we are using the word roots, then in the complete program that we are writing below, roots will have the same meaning as that of whatever we have defined on the top. But in Sage, there can be a function called roots, but that will become unavailable to us in this worksheet. Okay, that's the problem with if your definition conflicts with an existing definition available in SageMath. So the Google sheet is updated, Google document is updated, please see. Okay, now there is an interesting problem in which text it was. I think calculus by Howard Anden. No, SageMath for. So this problem, next problem is actually taken from SageMath advice for calculus. I think what is the SageMath TM? I don't know. Next problem I am taking from this text. I think this TM is trademark, SageMath, that's enough. So the problem is nothing but finding horizontal tangents. So what is horizontal tangents? Tangents that are parallel to the x-axis. So the problem is essentially that maybe to sin x itself we can find horizontal tangents. Let us try to see. Suppose that we take f of x equal to sin x. This problem is not actually from this advice for calculus. Maybe in the beginning I will try to do a simple problem, but if I do that simple problem I will not be able to demonstrate everything that I want. Therefore, okay, let me just take the same problem itself. So the function I am taking is square root of, this function is taken from this particular problem, which I am going to with the number square root of 2x4 x to the power 4 minus 2x minus plus 1 divided by, okay, so I should put a bracket here, divided by 2x4 plus 2x plus 1. Everything is in square root. So this is the function. So if you want to see the function in the math notation, the function is here. Oh, sorry, plus. This is the function. Okay. So if you want to actually check if there are some horizontal tangents or not, what we can do is that we can try to plot this function. Okay, we can try to plot this function. Plot. So always we have to mix up tools. We have interchanging. We have to interchangeably use several tools in such a way that we should try to understand the problem in a better way before trying to attempting to solving it. So a plot is actually a very good choice for understanding what exactly, how exactly the function looks like. So plot fx, I'm not specifying any range, but anyway, maybe -2 to 2 is probably a good choice. The plot is here. You can see that there are possible horizontal tangents like something in the range -1 to 0.5. If this point is differentiable, what is this point? I don't know what exactly is this. -1 to 0.5. This is not a sharp edge. I guess that this is, of course, a sharp turning is there. This is not a sharp corner. Anyhow, -1 and -0.5 there is a point, and 0.5 and 1 there is another point. At least 2 points are there where horizontal tangents are quite possible. Maybe we can try to zoom to -1 0.5 to see -1 0.5, zooming it. Yeah, it looks like a little bit what you call the turning of that curve doesn't look that much sharp now. Okay, so in -2, maybe we can try to expand this function and see if there are any other horizontal tangent points. That's also quite possible. -3 to 3, if you try. It doesn't look like so, but anyway, it seems that the horizontal tangents are most probably in the range -1, 0.5 and 0.1 somewhere. Okay, that's what we can guess from these two lines of computation. So what we have to do now? So we have to now find the derivative of fx. Let us call that to be f1x instead of f dash x. F1x is equal to derivative of fx with respect to x is not necessary, I guess. I'm trying to even show that. What happened to our plot? I think plot vanished. Maybe we should put even a show here. Yeah. And the function is, of course, a little bit complicated function. The derivative is. Now, let us try to even plot that derivative of x, derivative of fx. So, the point now to remember is that the tangent becomes horizontal provided that the slope of the curve at that particular point is 0. The slope of the curve is the derivative. Slope of the curve is given by the derivative function. Therefore, if we check for the points where the derivative is 0, at those points the tangent is going to be horizontal. That's what the logic is. Trying to solve the derivative equal to 0. F1 roots. Solve. For x and print f1 roots. Let's see if the points are actually matching with what we have guessed. That is between -1 and 0.5 and 0 and 1. Let's see that. So two roots seems to be complex roots, right? Complex conjugates they are. And the other roots, it's difficult to actually make out from this. Maybe we can try to approximate it, numerical approximation. If we do that, what will be? Oh, that's not the correct way to do things probably. Or maybe we can do something else. For R in F1 roots. Okay, there is the roots are actually some symbolic kind of expressions with x double equal to etc. etc. We need to take the right hand side and try to evaluate it numerically. Print n of R dot RHS. So what are the right sides? First is minus 0.63, second is plus 0.63. These two are the points where the derivative becomes 0. So that actually matches with our that previous guess. It is between minus 0.5 and minus 1 and between 0 and 1. These two are matching. So the 2 points where the tangent becomes horizontal is these 2 points. Now, okay, what are the real roots now? So how do we filter out all the complex roots? Any idea? We have got real as well as complex roots, but we want to try only with real roots. The horizontal tangents at the real root because at the complex root we cannot evaluate the tangent. So how do we find out? Real f, real root f1. Suppose that we start with an empty list. here itself. If R is in RR, which essentially means that if R is a real number. Sorry, that's not the correct thing. This is in RR, that's correct. If R dot RHS is in RR, we will push that root to real root self. So now we can see what are the real roots actually, again as a list, but real roots only. Real roots of f dash are these two. Is not necessary, sorry. But why we are getting only one real root? Oh, sorry. We have not looped. So we should have again gone through all the roots. Yeah, this is what we have to do. Real roots are these two. Now if we want the numerical approximation, then we can do that approximation here itself. If you want the actual number, the two real roots are here. Okay, let me update the Google document with all these.
Sir, I have one question.
Yes, please.
Sir, why you using that last for loop? We are already getting the real loops using the previous for loop.
Sorry, we are already getting what?
The real loops, right? From the previous for loop, that all that real loops. But again,
are we getting only real roots? We are getting complex roots as well.
Okay, well, that the I is there.
Yes.
Okay.
The capital I corresponds to the imaginary number I.
Okay.
Sorry, I didn't mention that. I forgot to mention that. That capital I corresponds to our square root of -1 complex number. That's denoted by capital I in Sage.
Okay.
Right. So we want to filter out all the complex roots. That's why we did this. Okay. Now we got all the real roots. Now suppose that we want to draw tangent line at this these are the horizontal at these points you can see horizontal tangent lines. So how do we draw the horizontal tangent line now? So we have already seen that how to draw that. Okay, tangent line, the equation we know that, right? Tangent line at x fx or xy or x naught fx naught to be f of x naught, that is y equal to y equal to the equation of the tangent line is nothing but y equal to, or okay, whatever you want you already have the one coordinate is already there, x of x is already there. Since you know that it's a horizontal tangent line, there is nothing actually, because all you have already found the slope to be equal to 0. You need to just connect some point to the left of that the horizontal tangent point to the left of that point. When you have one of the point, you have to take to the right of that also, you have to take some point. It's very easy because essentially you already have the y value there, and since it's a horizontal tangent, for getting the x value, what you have to do is corresponding to y you will be having an x, and just take keeping the y fixed, just reduce some epsilon from that x and add some epsilon to that x, so that you will get left and right endpoints of a line segment passing through the tangent line. So drawing the tangent line is not very attractive here because it's already the horizontal tangent, right? There is nothing to find Slope is not necessary to find here. Slope is already 0. Okay. Now, if you want to draw the tangent line, what you can do is, okay, I'll just explain that also if it's not very clear to all of you. So, the tangent line at which point we want to see? So, tangent line at the points where the real roots are actually occurring. So, real roots are, this is x. So, correspondingly we have y. So, tangent lines are, so we will draw both the tangent lines for r in real roots f1. So, take each tangent line. Now, this is the x value. Corresponding y value we can find by substituting this x value to f of x. Y equal to f of r. We found that x is already here. X is equal to r if you want to again specifically say x equal to r. Y is this. Now, if you want to join a line connecting these 2 points, connecting going through that this particular xy and parallel to the x-axis, then what you can do is you just take x minus some epsilon, right? X minus some epsilon, x plus some epsilon, and plot a line between x minus epsilon y and x plus epsilon y. P plus equal to, so what is P? Let us plot, okay, let us change this. P equal to, or show, to this P we will add what we are supposed to add, line. So what is the structure of the line command? Line, I think x1 y1 x2 y2, right? That's what we have seen previously, x1 y1 x2 y2. So instead of x1 y1 we have x minus, so take epsilon to be equal to, maybe we can take even to be equal to 1, x minus 1, the coordinates are x minus 1 y and x plus 1 y. So that is the first plot. Oh, this is not required, sorry. Okay, that's the first line. Now, so assume that the 2 tangent lines are already drawn. So let us just show the plot. Okay, that we are supposed to give as a list. So this is correct now.
Hello.
Yes. Yeah.
Hello, buffalo.
Yeah. Hello. Okay, I think we have completed that horizontal line. If we want, we can give some different color also. So that doesn't color equal to, since the x coordinates are changing. by r. Or RGB color, what is that command? I don't know. I forgot that command name. Color equal to, okay, let me just try with red. Then probably in the line that color is not there, it seems. I think RGB color is what we can give here. RGB.
The color is showing in the picture.
But I am not seeing anywhere. Where is that? Oh, sorry. I was checking the top one, right? Sorry. That's correct. Previously also it was showing.
Hopefully, sir.
Okay, let me just see. I was checking the top picture. Right. Thank you. Correct. So these two are the horizontal tangents. So we can draw not only horizontal tangent, we can draw any tangent, of course, in this way. But here the good thing was that we did not have to go find out what the slope was, because it is already found to be the horizontal tangent. Okay, let me update the entire thing in the Google Sheet. Updated the complete thing. So I have updated the Google document. You can have a look at that. Okay, so this is actually, as I told, it's a problem taken from this particular book. It's a very good book for problems in calculus, and many of the problems he has attempted using SageMath, but of course some of the problems are a little bit complicated, but if you try to derive your own problem using the already available problems in that textbook, that'll be a much better thing to understand things properly. But if you try to do the problems as given already there, it can be confusing to you. Okay, so now we are moving towards a maximum minima problem. So as I told, to find relative maximum, relative minimum, what we essentially do is we know that relative maximum, relative minimum, etc. exists at the critical points, right? Critical points are non-differentiable points or derivative becomes equal to 0. And suppose that f is a function which has second derivative up to that existing, and suppose that point at which f dash vanishes. So that means that f dash becomes equal to 0. So if at that particular point we know that if the second derivative is greater than 0, then f has a local minimum, and if the second derivative is less than 0, then f has a local maximum. So essentially in the physical terms, in the physical sciences terms, what we are saying is if the acceleration is positive and the derivative has become 0, it essentially means that So the acceleration is positive. So what does that mean? Acceleration is positive means that the function is going to increase. But now it's 0, therefore it's a local minimum. Acceleration is negative means that the function is going to decrease. Now it has become 0. Therefore, we are at a local maximum. That's what essentially it means. So we need to evaluate second derivatives at critical points, right? That's what we want to see. And we want to make a conclusion from that. Okay, so let us try to do one problem. So next is critical points and second derivative. These two are the major tools that we are going to employ here. I'm defining a function, a polynomial function, f of x equal to x cube minus 3x plus 2. To see if it has some minimum maximum in the within some finite range, we can try to plot it. Plot f, say in the range minus 10 to 10 to get a large picture. So it seems actually that it's crossing the x-axis at least 2 times is what we can see. That is within minus 5 and 5. Therefore, not only crosses that the graph becomes horizontal to the x-axis in the range minus 5 to 5. If you want to have a zoomed look, maybe we can try with this minus 5, 5 here. So we have a better picture. Now it seems that it is between minus 2 and 2. To get again a zoomed picture, maybe we can try with minus 2 and 2. Yeah, that picture probably gives us a very good view of what exactly we have to do. So we are trying to, most probably what happens is it's around minus 1 and around plus 1, the function actually becomes horizontal to the x-axis, and therefore they are probably the critical points. So being said that much, of course from the graph we cannot completely make out a final conclusion. We need to do the calculus here. The calculus means that find the derivative, and this is a polynomial function, therefore there is no issue of non-differentiability, right, anywhere. So what we are supposed to do is just to take the second derivative, just take the first derivative and see if it's becoming 0 or not. Here for next, we can directly do that. Critical point, let us put the name CPS. So solve derivative of f equal to 0 for x, right? What are the critical points? The points as we guessed, it's minus 1 and 1. So at these 2 points, the derivative becomes 0. Let me update the Google document after this. Done. You may try with your own code in your own system. Okay, now we are trying to find the second derivative and see if it's greater than 0 or less than 0. So we need to check at these critical points, right? But at these critical points we need to, there is one small problem that we will be having. We need to take the RHS, right? CPS values. So we don't know, first of all, how many are there? There are 2. So CPS values is empty for C in CPS. CPS values append C dot RHS. Let's do that. Now see that CPS values are these 2, -1 and 1. Okay, now what is the next thing that we are supposed to see? So at these points we need to evaluate def double dash x for, okay, otherwise we can directly also do it from here itself to see that if it's so maybe from here itself we can say, instead of going into another loop, if see that we need to evaluate, we need to find f double dash x and evaluate. So let us find the f double dash here, f2 x equal to derivative of fx with respect to x 2 times. So this is the second derivative. If f2 dot subs x equal to, this is how we are supposed to do this. Suppose that we are substituting for x equal to c dot RHS, where c is the first root. If this is greater than 0, what we wanted to see is at which value c dot RHS f as a. So if it's greater than 0, what we have said is f as a minimum. Okay, so elif, if it's less than 0, remember that can be equal to 0, and in that equal to 0 situation we are not conclusive, we don't have any conclusion. F as a maybe log. This is not essential. Removing and trying to see the points. At -1 there is a maximum. Yes, there is a maximum. At +1 there is a minimum. Seems to be correct from the picture. I have updated the Google document for this. Please see. So this is how we find the local maximum, relative extremum. In this way we can locate. So now if we want to find the absolute maximum, absolute minimum, that's what we have to do is we have to take relative maximum, list of relative maximum, and then we are supposed to take the maximum of the relative maximum. That's what it is. And not only that, at the endpoint, since at the endpoints the function differentiability is under question, at the endpoints also we need to evaluate and we need to check if at the endpoints if the values are more or less compared to the critical points. So in this way we can find out, we can determine, we can solve the maximum minimum problem using SageMath. Okay, so that's it. Now we can even determine the point of inflection, right? Point of inflection, how do we determine? So the point of inflection is that from the, so it's said to be a point of inflection if it's increasing on the left and decreasing on the right. So it essentially means that the direction of the curve is changing, right? The increasing, decreasing, if that phenomena is changing, then we say that it's a point of inflection. Right. So let us do that part also. So maximum minima we have done. So point of inflection also we will see. So for determining the point of inflection, what we are supposed to do is we have to check if the second derivative is at x equal to a, if the second derivative is positive at that x equal to a, it's concave up at that point. If it's less than 0, the second derivative is less than 0, it's concave down. So we say that a point is a point of inflection provided that to the left of that it's concave up and right of that is concave down, or the other way. So the direction of moving is changing, or in one direction it holds water and in the other direction it doesn't. Okay, or in one direction if the point is inside the curve, and in other direction is the point is on the top of the curve. Okay, that's what we are supposed to do. So we need to check f double dash and see if f double dash is greater than 0 at one particular point, and okay, so to the left of that point we need f double dash to be less than 0 and greater than 0, right? That's what we want. So essentially what we need to do is we need to take a point in between the two critical points, take another point in the next critical point interval. For example, suppose that we have A1, A2, A3 as 3 critical points. So we have to take A1 and A2 in between. We need to choose a point. Find if f double dash x. Remember that f double dash x becomes 0 at these critical points. That's what we are assuming, right? It's a local maximum or local minimum. Suppose we have found the point a1, a2, a3 to be in such a way that at these points second derivative is 0. Now we are going to check if the function is convex or concave between a1 and a2, a2 and a3. So for that, take a point in between a1 and a2 and a2 and a3. If these 2 points, at these 2 points, if f double dash is changing the sign, then the point what do you call that particular critical point is a point of inflection, right? Not exactly that point of inflection. Okay, let us try to do this problem, right? So let us take another problem where there are already here we have what type of curve we have already plotted. So I think yes, here also the direction is changing, because in this direction it's in one direction, and here we are changing the direction. Therefore, I guess that we will be having a point of inflection. But where that point of inflection is, that's the question. Okay. So f double dash x equal to 0 is the point that we have to locate. So let us mark the point, continuing with the same problem. Let us mark the points where f double dash is 0. Have we located that? No. Let's mark the points. f2 roots, f2 equal to solve. f2 is already here. f2 x equal to 0 for x. And values we need. So we need to essentially take an empty list and fill the list with only values. Oh, sorry, this one. Now fill it with values. So what are the values? Print. So it's 0. Let's plot it. Point for R in, of course there is only one point, but making the program a little bit more general, plotting the point R comma f of R. Take the size to be something large. It's here. This is the point of inflection that we are seeing. This is a possible point of inflection, not the point of inflection where f2x is equal to 0. So let us add a note also. Possible point of inflection. So we need to check if we have, to the left and right of this point, we have what you call different signs. To the left and right, essentially what we can do is that we can take some small epsilon once again. So if f2 of or f2 substitute, what is the point? F2 substitute So anyway, we know that there is only one point. So essentially we can simply check uh, 0 minus 0.1. I think we can use the SGN function, SGN. So this and the value at plus 0.1 to the left and right. So we will conclude since already the value is known to us. Else not a point of inflection. Subs for substitute. What's happening here? X equal to, sorry, x equal to, one second. Hey, what is this? No canonical, where is that else? Where is that happening? SGN substituted. There is one bracket is extra here or what? No. This is not. This is actually the F bracket. No. For sign, should I use sign straight away? What's happening here? Okay, let me just see. Come down. No canonical coerce function with argument to symbolic ring. So what is our F2 here? Or should I just use F2 of X instead? Okay, 0 is a point of inflection. That's it. Of course, if there are more points where F2 becomes 0, we need to programmatically again do. You have to again check all these points. So you can probably think about how to do that. Second derivative, point of inflection, everything. Done. See that when I am copying and pasting from the worksheet to the Google document, there is some problem with the alignment. But when I am giving the direct worksheet to you as an IPython notebook file, there is no such problem. So if you are doing it now itself, if there is some error in the indentation, please check that carefully. So I have updated the Google document with all this. So we have done that complete problem, finding maximum, minimum, relative maximum, minimum, locating points of inflection, everything.
Sir, can you please share the link?
Google document link.
Yes.
Yeah, I'm doing it once again. See. So now for finding, okay, we can just try to see. Okay, for finding approximate rules, we can use the provide, since we know that how to find the derivative of a function, and we know how to evaluate, how to solve for roots, etc. So we can try to find approximate roots using Newton's method here, right? Newton's method, it's a bisection method, and there is bisection method as well as there is a derivative method. Okay, let us try to use the derivative method. So which essentially means that find out the derivative and take the first root to be anything, right? Some x naught. After that, take the second root to be x naught minus f of x naught by f dash x naught. That's what Newton's method suggests. Okay, let's try to do that. Let's try to see that first of all. Approximately roots. So essentially we have xn plus 1 equal to xn minus f of xn by f dash x. This is what we essentially want. This is the method we have, and we'll try to stop. We'll stop after a few iterations. Either we can stop it after a few iterations, or what we can do is we can determine one error level, so that when fx becomes very close to 0, we will stop. When fxn becomes very close to 0, we will stop. So either way we can do. So let's take a polynomial. F of x equal to x cube minus x minus 1. Let's see if it has some real root at all. By product. In the range, say minus 5 to 5, a reasonably large range. Yes, it seems to cross the x-axis 2 times between minus 2 and 2. So we can start. Remember that Newton's approximation will be giving you only one root, right? One approximate root. So where do we start? So anywhere we can start. So essentially what we have to do is we usually start at, we locate a point where f of x is possibly negative. We locate a point where f of x is possibly positive, and we choose the midpoint of that to be something, the beginning root, the first root, the initial approximation. So maybe we can choose x to be equal to 0 as the initial approximation, or x naught to be 0. If we choose x naught to be the initial approximation, then x1 is nothing but x naught minus f of x1. Remember that. So f of x1 we can find by substitution. X equal to x naught by derivative of f at x, and evaluate, substitute at x equal to x1, oh sorry, x naught, there is no x1 as of now. This is complete. And see what this x1 is. X equal to -1 is the root, is what it says. The initial approximation. Let us try to, okay, let us try to see the plot within the range -2 to 2 to have a closer look. Maybe we can even try to draw that. Mark that point on the curve itself. So let's start with the P. P is this. P plus point, which point we are supposed to add, x1, f dot x1, and see the plot. Maybe the size is very small by default, take it to be some 30, and color black. So this is the point, and we can see that this is nowhere close to the approximation. If we start with a different approximation like 1, we will get something, the initial approximation to be something else. Okay, it depends upon the initial approximation. Okay, what next? So we are going to continue with this. So now we are going to continue with the same procedure. Let us do it. Let's do two steps, and after that we will try to convert it into a loop.
Excuse me, sir. I have one question.
Yes, please.
While plotting 2 points or maybe 2 curves together, we usually put plus. No? So now in this case, y equal to is also included.
Where?
P plus equal to.
So see that already P consists of a plot, right?
Yeah.
So when P already has, suppose that P is a number, P consists of a number, suppose that P is equal to 4. When I say P plus equal to 6, it means that add 6 to whatever value is already existing in P.
Okay.
Otherwise, it will be completely erased. So this point will be added to the already existing plot. Okay, that's it. So P plus equal to, it has the same meaning as P equal to P plus point. So that's the meaning of this. So whatever was previously existing, add that. So see that whenever we are writing something on the right side, its value is taken. Whenever we are writing something on the left side, it's treated as a variable. So if P is appearing here on the right side, it will not be treated as a variable, but it will be treated as a value of P. But when P is written here, it is just again once again a variable. So we are using the same variable for storing the value of the plot plus point. That's it. Why is it appearing twice? Okay, x2. x2, x2. See that it's becoming closer. If we start with as previously, it's coming like this, right? Okay, so now to do all these things, okay, let me just update the Google document with all this. We will try to automate this process in a loop, but before that I am updating the Google document. Okay, so to automate this entire process, okay, I'm just copying and pasting. I'm just leaving it like this here, and I'm copying and pasting this thing here. Now, how do we want to automate? We want to check if the value of f of x is close to 0 by epsilon, or otherwise the value of f of x minus 0 is less than some epsilon, or essentially f of x is less than epsilon, modulus of. Okay, so let us fix some error boundary equal to 0.1. So if fx becomes, instead of 0, if fx becomes 0, fx becomes 0.1, that essentially means that this is an approximate root. Okay, it's moving towards, see, we are assuming that Newton's method actually gives you a sequence of roots that are converging to the actual root. Okay, that assumption is always there. Otherwise, you may think that, okay, if you are getting one root, now if you are getting f of x to be 0.1, what is the guarantee that in the next step that will become something very much closer than 0.1? So we are assuming the theoretical foundations of Newton's method, and the theoretical foundation says that definitely this method will converge to the root. So we are assuming that. So except the initial approximation, let us take the initial approximation to be a, or okay, whatever. After that, what we are supposed to do, we are supposed to keep on changing, or x naught itself here. Now we are supposed to change while what we are supposed to do, f of a, or absolute value, because it can be negative also. Absolute value of f of a is greater than epsilon. So which essentially means that we are not close to 0 by less than epsilon. Less than or equal to epsilon, we are greater than epsilon. When it is greater than or equal to epsilon, we will find a new root. What is that new root? x1 or x0.
So there should be a semicolon after while loop.
Yes, that's correct. Thank you.
And I think there's also error in the spelling of epsilon.
Error in what? Right. Second one. Right.
Spelling and file.
Yes, correct. Thank you. So while this is happening, what we will do is we will keep on constructing newer roots. So new root is found. So what is next? Now what we are supposed to do is we need to interchange the value of, so we have a new x1. So at the place of x0, now we are going to use, instead of x0, the x1 value. Or here itself we can actually try x0 equal to the new x0. Right, this is good enough. Changing the value of x0 with x0 minus f of substitute x0, that's it. This is enough. You can even use a. A is the initial root. Change the root to, change it to the new approximation. A. Let's see. Let's try to plot that point also. So initially we will plot with the original A, maybe we can do it later. Let's see the final plot. So it seems to be in a loop. We have done something wrong. So what we might have done, okay, now it's a time to interrupt the kernel. So you can see that there is an hourglass icon here. Right? I'm just trying to interrupt. It's interrupted. What is this? What is the problem? P equal to, where is this happening? A f of, substitute this. Oh, I think too many plots are happening. Most probably that's the reason. Okay, anyway, I will try to stop that. What is the result of this? Interrupting once again. Okay, let's try to do one thing. Let's try to do this 2 times and see what this f of x is. Print AFA again, AFA, AFA, AFA. What are the values? We probably need numerical values. In 4 steps, what's happening? There is something wrong with all these things. Okay, so what we have done? Xn f dash xn plus 1 equal to. So what we have done here, xn plus 1, the same number we are choosing as xn plus 1, xn minus f of xn by f dash xn. So we started with 0, we got minus 1, minus 6.25, but suddenly it jumped to this minus 25. How did that happen? What's the reason for that? A equal to A minus f of A by f dash A. I think is that maybe, I don't know whether the diff is taking priority or the other function is taking priority. Let us anyway put this here and see if the result is anyway different. This is xn plus 1 equal to xn minus f of xn by f dash xn. What is the problem here? Okay, let's see once. What is derivative of f? 3x square minus 1. Okay, that's perfect. Okay, that seems to be okay, fine. Okay, let us try to do it 2-3 times more. Okay, it's moving. Oh, what's happening here? It became too large. So this is the closest value that we are getting, but at -1/2. Okay, let us start with 1 and see if the same thing is happening. I think here it's converging because we are doing it again and again. That's why it's giving some wrong answer, but it is not actually the correct thing to do, correct thing to happen. So yeah, here it's converging. I think is it because of a bad choice of the initial approximation? Okay, now let us try with 1 and see if this is working fine. If the absolute value is okay, I have not asked for printing anything, right? Show P and the I think it's because of but that is not actually correct thing. So even a bad choice would have okay, what I guessed is that here, because the function is moving away from 0, that's because of that only I think it's happening like that. So essentially for all these things, what we can do is we can try to locate okay, we need not actually go for a value. Okay, I don't understand why it's like that. Somehow when we are choosing a different initial approximation, it's going away, it's not coming close to that value. 0.001 if you choose. This is 9.23 into 10 to the power -7. This is also, it's also fine. But what about 2? Approximation with 2, that's also converging. Okay, I think because we are choosing a value to be equal to 0, there is a problem because 0 is close to that and after that it's again going away. Something like that is happening. Okay, that's the only final guess I can make about this. So this is how we can do it in a loop. I am updating the Google document with all this. Please see. Okay, now I think an approximation, that method is also now seen. Now we will go to what you call we'll try to find, I think, as per the workshop schedule that we already have, we are trying to discuss something related to computing Taylor and Maclaurin's polynomial. Okay, the Taylor polynomial we'll try to create. Taylor series essentially. So see that to find out the Taylor series or Maclaurin series, the Maclaurin series is nothing but the Taylor series actually become at x equals 0, if we take the Maclaurin series, it becomes, sorry, at x equals 0, if we take the Taylor series, it becomes Maclaurin series. Therefore, essentially what we are supposed to do is we are supposed to find out an expansion of the form f of x equal to f naught f of x naught plus f dash x naught into x minus x naught plus f double dash x naught. Okay, that's it. So we have already seen how to compute all these derivatives. Now what we are going to trying to see is we will try to see that how does the curve look compared to the original curve. Okay, the original curve is already known to us. We are trying to differentiate that, and how does this Taylor series approximation and the actual curve how they are related, how close they are. Try to see that. Taylor series approximation. Suppose that we take f of x to be equal to maybe the very non-function sin x itself. After that we can change it to anything. Suppose that we want to evaluate, we want to find the approximation of sin x around x equal to pi by 2. So how do we do that? We need to find out the expansion. So series of, suppose that we initially take it to be just an empty list, to that we will keep on adding the components. So f of x naught, x minus x naught into f dash x naught, x minus x naught the whole square by 2 factorial f double dash x naught, etc. in a loop. 4. So how many times? Let's try to keep 5 times. So which essentially means that up to the 4th derivative we are supposed to find. So what are we supposed to add in loop? To the series of, we are supposed to append. What should we append? So the first time we can actually take it to be f of x naught itself. There is nothing else to do. Second time onwards we will try to compute. So what we are supposed to append, x minus x naught star or by, so we are supposed to take from first derivative to 4th derivative, right? So for 4 times in range 1, 5. Remember that range 1, 5 essentially means that 1 is included and 5 is not included, right? It's left open, it's left closed, right open. X minus n factorial. This is on the top. So x minus x naught star derivative of f with respect to x, and the order is also important, nth derivative, and we are supposed to evaluate it. Substituting x equal to x naught. So I hope that this is complete. X minus x naught, we are appending x minus x naught into the nth derivative evaluated at x naught by n factorial. I think this is good enough. Let's try to see what this series f is. So the first time appended is just 1, because we can see that this is sin pi by 2. Second time is 0. So second, fourth times are all 0. All the even times are 0, right? So 1 plus 1 by 4 pi. Okay, let us just try to sum it and see. This is completely wrong. What is this? This is correct. One plus so derivative 1 oh sorry that the power is missing from here, right? It's x minus x naught the whole to the power n, that's missing, sorry. What is this x minus x naught? So the formula, the Taylor series is that f of x naught plus f dash x naught, which is first derivative, into x minus x naught, f double dash x naught by 2 factorial x minus x naught square. So etc. We are supposed to go on like that. So what's happening here? F of x naught, that's fine, and okay, let us try to see what exactly is happening here. I don't know, maybe this is correct. I don't. So, okay, we are, oh, sorry. I think I am getting confused with the Maclaurin series. Okay, let me just try with the Maclaurin series to see if it's correct or not. So, is this correct? This Maclaurin series? Okay, let us try to, I think, sorry. Very sorry, I was getting confused with Maclaurin series. I was trying to get a very familiar expression for sin x, but I didn't realize that that expression is at x equal to 0. That expression is around x equal to 0. Okay, let us try to take some 10 times and see. Yeah, this is correct only. I think this is correct. Fine. So at pi by 2, this is the expression. But anyway, we want to have a plot also, right? We want to actually have a plot of how does it actually look. At each and every step, shall we try? Just with 3 approximations, 3 steps, 3 sums. Okay, let us take the original plot to be equal to sin x. Okay, let's try. P equal to plot sin x in the range. So where we have taken pi by 2. So 0 to pi. Try with that and see how does it look. So the first plot we will add. This is not required. So the first plot, how do we plot? P plus equal to this sum of series is the Taylor series for us. This is the Taylor series. Taylor series is this. So we are supposed to plot this Taylor series. In this range. And now see the plot. So we can see that the initial curve is nothing but it's maybe we can turn on legend also, but it's not changing the color. That's what I'm wondering. So otherwise I would have use a color command here, color or hue, and turn on legend. Hue equal to 1 by n. So we have different colors. Now turn on legend. Approximation maybe we can put n here. Okay, the original approximation is not there, but why is that original approximation missing? I think we have, yes, we have only the beginning also we are supposed to do some approximation. Even then we will be getting only 2. Or otherwise we can put approximation 0 here. This is the original curve, right? Original curve. Let's keep it here itself. Approximation 1, where is the original curve? The original curve is the blue one. Approximation 1 is the straight line because it's a linear polynomial. Approximation 2, which is a quadratic polynomial, which is almost a parabola and it's very close. And if you go for one more approximation, suppose we take 4, we will be getting one more approximation, which is the green one. But what happened in one of the approximations? I think it got merged inside another one. So if you try with 5, okay, fifth one is almost close, right? You can see that fifth one is almost on the sine curve. Maybe we can use dotted so that we can see it easily. And sine curve probably with some thickness extra. Oh, the thickness extra will not actually help. can say that I think the fourth approximation, approximation 4 is almost on the curve. It's almost on the curve. Now, okay, we will try to see one more thing. So here we have taken the range 0 to pi. So let us take left endpoint LE as minus pi by 2, right endpoint as pi by 2 of the plotting interval. And let's try to plot it in that interval instead of plotting it around 0 pi, where at pi by 2 we have evaluated. Let us try to plot it around minus pi to pi and see left endpoint, right endpoint. So to see whether the approximation is accurate at around the other points as well or not. You see this, that around pi by 2 the approximation is becoming very close to the curve around this point between 1 and 2. But away from pi by 2, what happens is that the curves are they are at different distances. You can see that the approximation 4 when it moves away from 0, approximation 4 also moves away from the actual sine curve. See this. Therefore, the Taylor series approximation, if you are approximating it at around one particular value, the approximation is going to be valid only around that particular value. So if it's at pi by 2, that expression you may use only around pi by 2. So just like that, if your Maclaurin series is around 0, if you try to evaluate the sine function not around 0, that's not going to work. Around 0, the approximation is going to be correct. You can find any value of sine around 0, but away from 0, if you use the Maclaurin series, that's going to be disastrous. That may not converge to the actual value. Okay, so this is the lesson that we can understand from this problem, all these plots. Okay, let me update the Google document. Done. Okay, I hope that this problem is somewhat interesting to all of you, because we are trying to, most of the times what we do is that we try to understand the problem only from the theoretical point of view, but here by evaluating the Taylor series and trying to plot it away from the point where where the series is constructed, we are actually getting a lot of insights into the problem. Okay, I think now we will go into something that that I have probably promised to discuss today. That's about something related to vector calculus. We will try to start something related to vector calculus, because tomorrow also we have to go to multivariable calculus, which is more or less closely associated with this vector calculus. Therefore, we start those things today. We will not be able to go too far, but we will start. To start with doing all these things, I think so initially. So what are the things that we want to discuss? Divergence, curl, dot product. Okay. So what is the schedule that we have? After that, matrix algebra, number theory, problems, complex polynomials, abstract algebra, permutation, operations, plotting, plotting in vectors, vector field plotting, gradients. So gradients is already there. So anyway, I will try to define a few things, not everything, because some of the things are going to come towards the end of the series where we have vector field plotting and gradients. Okay. So to start with doing certain things in the vector calculus, there is actually a built-in function called vector in SageMath, using which you can actually define a vector. See that vector actually can be defined as a tuple also, but if you are defining using the vector command itself, there are certain extra advantages that we have. Okay, let us try to see how to define that first of all. I'm defining a vector first. Okay, with Sage, as I told already, we can convert the cells into some marking cells, some markdown cells. Here I have converted this cell to a markdown set, using which you can write some, you can use some HTML code to make some bold text, etc. But computations cannot be performed in this cells. Let me make a heading 1 of type 1, heading 1. I'm doing this just to demonstrate that this is also possible. See that you get some bold. Not only bold, it's first type header. So vector calculus, and after that just evaluate as usual. So let us define u to be a vector. U to be the vector. Which vector we will take? For defining a vector, we are supposed to define it as a list or tuple once again. After that, it will become automatically a vector. Let us define it to be 1, 2, 3. Suppose we define another vector v to be equal to 2, 1, 1. So 2 vectors. Now vectors can be added as usual, plus v. See that though we have written the list notation, vector is converting this to actually a vector. So you can even see that what type of object is this. Type of these two. This is in vector class. The added advantages is that you have certain automatic commands like dot product, cross product, etc. Otherwise, you may have to define dot product neuron. Of course, you can define dot product neuron, just you take the components and one by one you can define that. But instead of that, the dot product command itself is available to you. U dot product is here. Dot product is 7. Now similarly the cross product is also there. that's a vector. And you can straight away get the norm. You can straight away get the norm. This is square root of 4, and to get a unit vector in the direction of u, take let's see if it works, u by norm u. Yeah, it actually works. Or show but instead of using u by norm u, you can actually have u normalized. That also will work. I'm updating the Google document with all these. So updated. To find the angle between two vectors, now what you can do is you can see previously also we have done that, but now here we have the tools like norm, dot product, etc. available here. So if theta is the angle, then you need to take cos inverse of a dot b by or u dot v the cross the dot product divided by norm u star norm v. Angle between or if you want a numerical approximation, you can go for n 0.7 etc. Now if you want to see the plot of that vector, that can be directly done. Okay, let me see if you can do that directly. Plot u. That vector is here, but there is no arrow mark. Okay, so it's just a line. So if you want to add an arrow mark, then you need to only for two-dimensional vectors it's giving. Okay, two-dimensional vector also you can try. These are all three-dimensional vectors. Maybe one two-dimensional vector u2 equal to 1 2 and plot u2 what's happening here? Two lines. Oh, sorry. This is not. Sorry, that vector. Yes. Thank you. Vector is missing. Right. But the strange thing here is that SageMath, while plotting the vector in the 3 dimension, it is not giving the arrow mark. But in the 2 dimensions, it's showing the arrow mark. Somehow, I don't exactly know why it's like that. So you may have to manually put some arrow on the top of the already plotted line. There is no other way, it seems, directly. Okay, sorry, the feedback link is here. I'll post it to the YouTube thing also. So the feedback link is here. Of course, you can see the angle, so you can plot both these vectors, plot u2 plus, u2 plus, suppose that we take v3, what is that, v2, what we had taken as v, so 2 1 1, maybe we can take 2 1 alone, 2 1 and plot. If we plot u2 and v2, I think both should appear simultaneously, but it's not appearing. Maybe I should put it as a list. He's not interested in even that. Okay, then we will just how did we do that previously? Plot like this only, right? u2 comma v2. Okay, anyway, let us not do that, since we already have the plus command with us to see this is anyway working, and this is the so the angle between angle we have already found. So we can draw like this, and the arrow mark is of course here. And now okay, now to go into, so two vectors we have plotted already. Now in case suppose that you want to plot, so I will show that once. So suppose that this is in this is plot, and suppose we give an extra start equal to u2. What will happen now? See that it's plotted like this. So maybe for demonstrating the triangular law of vector addition, etc., we can try to do this. So sum of these two vectors, and here we can now plot sum of the third vector as well, u2 plus v2. To demonstrate the triangular law of vector addition, right? So this is also quite possible. Okay, let me just update the Google document, and probably I will stop here with this. Yes, updated. So we will continue with vector calculus. We will continue with probably vector calculus, and we will otherwise go to multivariable calculus, where we are going to define, where we are going to do some constrained optimization problems, some partial derivatives, some what you call multivariable calculus, where maxima minima are related to multivariable calculus in the surface related problems. All these things we will try to do tomorrow. Okay. So thank you very much. If there are any questions related to the topics that we have discussed today, you may please ask now. Thank you.
Thank you, sir.
Yesterday's worksheet is already uploaded to the link previously I had shared with all of you. I think the link is already there. I have not changed any link. I have actually shared the folder itself with you. So do you want me to share that folder once again with all of you?
Yes, sir, sure. Please share in group.
Okay, I will do that. The folder was completely shared with everyone. I will share that once again. That link once again I will give.
And thank you very much, sir, for mentioning my problem in vector calculus.
Right. Okay. Welcome. And we will be continuing with all these things, gradient and all these things. We will be definitely dealing with. But what I'm trying to do is tomorrow, once we do the multivariable calculus, we are in a position to deal with the gradient and all this kind of stuff. Okay. We'll be doing that.
Okay, sir. Okay. Thank you, sir.
Okay. Thank you very much.
Sir?
Yes. Please.
Sir, I have uninstalled and installed once again Sage 9.2.
Okay, what's the result?
First step I've done. It's not working again. The problem is same.
What about yeah.
I'll be uninstalling both now and installing the Sage.
No, that Anaconda you have not uninstalled, right?
Yeah, uninstalled, sir. Uninstalled and checked. It's not working.
See, you uninstalled and even after that it's not working?
No.
Okay. Then I am clueless. That I was under the impression that Anaconda is sharing the same path as well as that of SageMath, and that's why it's happening. Okay. So 9.2. So still there is no error, right? You are not getting any error also.
I'm not getting the output. I'm not. I mean this thing is not getting saved.
So okay, let us. Yours is that it's Windows 10 only, right?
Yes, sir.
Just 1 second. So
I would like to say something. Actually,
yes.
In my laptop also 9.2 was not working. So I have installed 9.1 version. Then it is working.
Oh, 9.1 is working for you?
Yes, the 9.1.
Oh, that's a great, that is a very good information, because the problem is that maybe the latest things are not compatible with some other drivers. So can you please try 9.1 as we told, because already there is, all these things are just...
yes, I have this.
Yeah, try.
Yes, sir, I'll try.
No,
I'll definitely try. So, ma'am, can you provide the link for the same?
Directly you can go there. All these things are in GIT Hub only. Yes, please. Please, ma'am.
Yes, sir. Actually, 9.2 was not working. So I have installed 9.1. 9.1 version.
9.1 is already...
It is working well.
Yeah, 9.1 or whatever version is, it's good enough for us, because most of the basic commands that we are dealing with can be done in most of these versions. If you go back to a much older version, then only that some problem can be there. These versions are all latest. So I will give you that link now itself. Just 1 second. Yeah, that link.
Yes, sir.
That link is you can get it from this link, this page. Please visit this page and you can download it from there.
Yeah.
Okay.
Okay, sir.
Okay. Thank you.
Thank you.
Thanks, sir. Thanks a lot.